Here we're going to talk about deviation from the ideal gas behavior. So if there are some factors that cause deviation from this ideal behavior and some of these assumptions that we made, and then talk about van der Waals equation and van der Waals interactions. So some factors that cause deviation from the ideal gas behavior. One of them is at high pressures. So high pressures is one of the scenarios that you should be wary of. So at high pressures, gas molecules are relatively close together. So this was a problem because one of those assumptions was that gas molecules occupy no volume. So only when the distances between the molecules are large is that really true, right? So at high pressures, this becomes less true as you get higher and higher pressures. So when the distances between these molecules are reduced, the volume occupied by each individual molecule becomes more significant since you have more molecules in a given space. So this is one of the scenarios, but we're talking about very, very high pressures for this to become a real issue, not just a few atmospheres, or even a compressed gas cylinder is not a high enough pressure. We're talking about maybe thousands of atmospheres of pressure, something very substantial in comparison. Also at low temperatures, gas molecules are moving very slowly. And one of the other assumptions that we had was that there was no intermolecular forces between gas molecules, either attractive or repulsive. When the gas molecules are moving very fast and the magnitude of their kinetic energies is much larger, then that will way overpower the magnitude of any of these intermolecular forces. So intermolecular forces are these attractive or repulsive forces between two individual gas molecules. So when the molecules are moving much more slowly, meaning low temperatures, they have much lower kinetic energy. So the magnitude of these forces becomes more significant. So if you recall, we have PV equals nRT. We can actually manipulate this just a little bit. So we have a pressure term and a volume term equals nRT. And we can deal with this just a little bit. So one of them would be the corrected pressure term. And A is something that you can look up in a table, for example. Same with B. So you can have this corrected pressure term and corrected volume term based on these factors if you are at a high pressure or a low temperature. So we're never actually going to be using this particular equation, but there are times where you would need to use something like this to get a much more accurate example. And again, ideal behavior in an ideal gas is something that's at normal temperatures and normal pressures. So we're really only deviating from the ideal if we have very, very low temperatures or very, very high pressures, or a combination of both of those. So that's really the only time where you would really need to use this. In most other scenarios, it's perfectly fine to not use that. So this is kind of what this is van der Waals equation. And like you can see here, this is a table that has A and B values associated with them for the particular gas. So this will be based on what gas it is you're using. And a lot of times they essentially don't play a big role. So that's why we've often ignored them. But you can see the gases do behave just slightly differently depending on what it is what exactly it is we're doing with it, right? So whether it's at a high pressure or a low temperature. Okay. So there's tables that you can look up these values if you were to actually be calculating with it. Really, let's just look at the trends. So one way to measure a gas's deviation from the ideal behavior is determine its compressibility factor, Z. So Z is PV divided by RT. For 1 mole of an ideal gas, Z is equal to 1 at all pressures and temperatures, right? Pressure and temperature did not change. PV over RT, that Z would not change in under those conditions. So here you can see this is characteristics of real gases versus the ideal gas. Ideal gas is staying completely still. But as you change the pressure, for example, you can see that pressure increase. You are seeing that we're deviating from the ideal gas actually quite a bit. So ammonia deviates a lot with that change in pressure. So it has maybe more intermolecular forces. So it's has attractive or repulsive forces that are more dramatic. But you see, we have to get to many atmospheres. So like even for ammonia, which seems to do a really poor job, it's not acting very ideally. You still have to get to something like probably 20 or 30 atmospheres before it starts mattering, and many of them are still do pretty well up to maybe 200 atmospheres, for example. So it really depends on the type of gas you're dealing with. Then likewise, also changing the temperature. So here, if you're increasing the pressure and let's say decreasing the temperature, so here 200 Kelvin, which is a colder temperature, you see we're deviating from the ideal a lot more at relatively low pressures. And up when you get closer to something like 500 Kelvin or 1000 Kelvin, it's getting closer and closer to the ideal gas. So this is just kind of how they would deviate. But again, it really matters with low, very low temperatures and high pressures. So most scenarios, we're not too concerned about it.